All right, I want to finish up this section on U substitution by showing you 3 different trick cases. I don't know if trick cases is the right phrase to use, but the idea is these are just problems that I wouldn't expect anybody to be able to solve. But if I show you how to solve them, then when you see a problem that's kind of similar, you'll have these new tools kind of in your back pocket to solve. But to be clear, looking at the 3 of these, I wouldn't expect anybody in this class to be able to solve any of these 3. If you can, good for you, but you certainly should not be expected to. So this first one, so you see this x squared here, and then the x plus 2 down here, and you might be tempted to be like, well, let's see, 1 less than this exponent of 2 would be an exponent of 1. So if my u is the x squared, then my du could kind of be the x. But there's a problem with that, right? My du needs to be times this entire thing. If my x were the du, I'd have kind of a du plus 2 underneath the radical. Like that wouldn't be right. That wouldn't fit my normal form of these indefinite integrals where the d and then whatever the variable is multiplied by the entire thing. So that's not going to work. It's not going to work to let u equal x squared. So what other options do I have? Well, I mean, I could let u equal x, but as I mentioned, that's never going to help because that doesn't do anything. I could try letting u equal x plus 2, or I could try letting u be the square root of x plus 2. If you try letting u be the square root of x plus 2, then when you take the derivative of that, it's going to be kind of a mess, right? Because x plus 2 to the 1/2 power, bring the 1/2 down in front, your du will involve x to the negative 1/2, so 1 over the square root of some stuff. That seems like that's going to be a disaster. It seems like the most plausible solution is to let u equal x plus 2. But you're like, but there's going to be a problem. That's not going to work. I know, but stick with me for a little bit. If u equals x plus 2, then du is just 1 dx, or just dx, right? So when I change my variables underneath the radical, I just have the square root of u, and the dx changes into a du, and this is all looking really, really promising, except for this x squared, right? We can't leave an x squared here because we can't have x's and u's. We need all of our variables to be the same, but I don't know how to get rid of x squared. I mean, I don't have x squared anywhere in here. Well, if u is x plus 2, right, maybe I can take this and be like, well, then x must be equal to u minus 2. Right, I could take this equation and subtract 2 from both sides to solve for x. Why would I want to do that? Well, because if x is u minus 2, then x squared is u minus 2 squared. So what I can do is I can change this x squared into u minus 2 squared. So this, evaluating this integral will be equivalent to evaluating this integral. And it's not obvious how this one is any better than this one, but it turns out it is. This one I don't think we can figure out in one step, but this one, if we do a little bit of algebra, I think we'll be able to figure it out. And specifically what we want to do is make this look more like a polynomial. We want to expand this u minus 2. So u minus 2 squared is u squared minus 4u plus 4. And then that entire thing needs to be multiplied by u to the 1/2 power, which is the same as the square root of u. And now I can take this u to the 1/2 and distribute it through my terms, and I get u to the 2nd power times u to the 1/2 power. When you multiply together exponents with the same base, you add up those exponents. So that would be u to the 5/2 power. And then I want to subtract from that 4u to the 3/2 power, that 3/2 being the sum of the 1 that's implied here in this 1/2. And then plus 4u to the 1/2 power. And this entire thing needs to be hit with a du. And this is an antiderivative that I can figure out. I'm going to be short on room. Maybe I'll go down here. The antiderivative of u to the 5/2 power will first add 1 to that exponent to make it 7/2, but then remember to multiply by the reciprocal of this exponent. In other words, throw a 2/7 down in front. Same idea here. The 3/2 changes into 5/2, but I need a 2/5 down in front. But that 2/5 times this -4 gives me -8/5. And then from this last term, I want to add 1 to the exponent to make it 3/2, but then I need a 2/3 down in front. And 2/3 times 8 gives me 8/3. And then if you can remember, toss on this plus c and be done with it. Really, this is more tedious than anything. The trick that I wanted to show you is this idea of letting u equal x plus 2. And then even though you might have other x's in the problem, you can solve for x in terms of u to substitute those in to change all of your variables into u's. Kind of clever, I guess. I don't know. Here's another problem that's also pretty tricky here. The idea for this one, I don't know, when I look at this, my gut instinct is, I don't know, the u should probably have something to do with this x to the 4th, either by itself or 1 minus x to the 4th. But then I quickly convince myself that that won't work because the du won't work out. If my u involves the x to the 4th, the du is going to involve x cubed, and I don't have an x cubed here, I just have an x. instead of trying to go down that path where your u is x to the fourth, what you want to do is recognize that this can be changed into one of those inverse trig ones. Right? Recognize that the antiderivative of arc sine of x is 1 over the square root of 1 minus x squared. And this kind of sort of looks like 1 over the square root of 1 minus x squared. The big problem is instead of an x squared here, I have x to the fourth power. However, if you think about x to the fourth power as x squared squared, I'll write it just so it's easier to visualize, then maybe you could start to see the substitutions. If I could make this x squared my variable, the variable u, well then the du would take care of the x and the dx, and I'd be left with 1 divided by the square root of 1 minus u squared, exactly what I need for arc sine. So the trick on this problem is to recognize that sometimes your u substitution isn't as apparent as you might think. Sometimes you either need to rewrite things or be really clever with your algebra to fit this into the right form. If I let u equal x squared, well then my du is 2x dx. In other words, half of du is equal to x dx. And I'm feeling good about that. Here's the x and here's the dx. I'm feeling a little sketchy over here. How's u going to be x squared? I don't have an x squared, right? But you got this x to the fourth. So if u is x squared, u squared is x to the fourth. So let's see, using all these substitutions, I'll make sure I leave plenty of room for everything. I have the square root of, and then instead of 1 minus x to the fourth, I could say it's 1 minus u squared. And then up in the numerator here, instead of an x, I can say, well, x and the dx go away if I introduce a 1/2 and a du. So I'll put the 1/2 over here, the 1 is a placeholder, and the du over here. You should go back and check that with these substitutions, this transforms into this. But if you can get this far, then things aren't too bad, because the antiderivative of 1 over the square root of 1 minus u squared is just arc sine of u. So this is just equal to 1/2 arc sine of u plus c. And if I change my u's into what I define them to be, x squared in this case, I get that this integral is equal to 1/2 arc sine of x squared plus c. Third and final example for this page is, it's a mess. This one's super duper hard. I even made it a definite integral. I don't know if that's a great idea, but I did. But just figuring out the indefinite integral is really tricky. I couldn't figure this out, if I'm being perfectly honest. I was like, what substitution are you doing there? Maybe if I messed with it long enough, I would have figured it out. But I cheated. I Googled it and figured it out. I was like, that's what they're doing. So when you stare at this thing, it's tempting to be like, well, there's not that much that my u could possibly be. So it kind of has to either be the square root of x, or 1 plus the square root of x, or the entire denominator here. It turns out that 1 plus the square root of x will work. And you might be skeptical that that works, because if you calculate du, the derivative of this, well, the 1 goes away. The derivative of the square root of x, that's going to be a disaster, right? Because this is x to the 1/2 power. So when I take the derivative, I bring that 1/2 down in front and then subtract 1 from the exponent. What I'm saying is du is 1/2 x to the negative 1/2 dx. And you certainly don't have a 1/2 x to the negative 1/2 floating around up here. All you have is this dx. But that's okay. I can solve for dx. I can multiply the 2 over to this side like I've been doing, and I'll also multiply x to the 1/2 over to this side. So I have 2x to the 1/2 du that's equal to dx. If you have a hard time seeing how the negative turns into a positive, this x to the negative 1/2, think about it as 1 divided by x to the positive 1/2. And then I multiply both sides, which moves it from the bottom on the right to the top on the left. At any rate, I get here. And you're like, wait a minute, this doesn't seem like it's going to work. 1 plus the square root of x will change into the u. And then my dx will change into 2x to the 1/2 du. I thought you couldn't have x's and u's in the same problem. And you're right, you can't. I cannot leave this x right here. But I have a relationship between the u's and the x's. U is equal to 1 plus the square root of x, and therefore u minus 1 is equal to the square root of x. In other words, x to the 1/2 power. So what I could say is 2 times, and then instead of writing x to the 1/2 power here, I could say u minus 1 du is equal to dx. Whoa, what just happened there? I chose my u in such a way that it gave me a really weird du. It involved an x that I didn't have in the problem. But rather than give up, I just kind of plowed through. I solved for dx, recognizing that my dx, when I substituted out the dx, would leave an x behind, and just hoped that my relationship between the u and the x would allow me to change that x into a u. if I use this line and this line to do my substitution, this integral becomes, let's see, my bounds of integration are zeros and ones, and be careful, those are x's. So I'm going to specify x equals 0 and x equals 1. And then instead of 1 over 1 plus the square root of x to the fourth, I'll say that 1 plus the square root of x is just u. So it's 1 over u to the fourth. And then instead of writing dx, I'll write 2u minus 1 du. And while this isn't the prettiest thing in the world, I think it's something I can deal with. Let's see if I can clean it up algebraically. I could pull the constant of 2 out in front, and then my integral still goes from x equals 0 to x equals 1. And then what I have left is u minus 1 over u to the fourth power du. You're like, not quite sure what to do with that. Well, allow me to help. Good old algebra comes into play again. U minus 1 over u to the fourth is the same as u over u to the fourth minus 1 over u to the fourth. Right? Because if you have a common denominator, you can just subtract the numerators and write the denominator one time. And the advantage to these guys is now I've broken it up into a sum, or I guess difference in this case, of two different terms, which works out pretty good for integration. I get that this is 2 times the integral from x equals 0 to 1 of u to the negative third power minus u to the negative fourth power. And that's because u over u to the fourth is the same as 1 over u cubed. I can cancel a u. And 1 over u cubed is the same as u to the negative third. And then 1 over u to the fourth changes into this u to the negative fourth. And now, finally, I can take the antiderivative and be in good shape. Antiderivative here, first I add 1 to the exponent. So that becomes u to the negative 2 power. But then I'm not done. I have to multiply by the reciprocal of that guy. Similarly, over here, I add 1 to the exponent, but then I'm not done. I have to multiply by the reciprocal of that new exponent. I'm going to evaluate that from x equals 0 to x equals 1. And that entire thing has to be multiplied by 2. You probably could evaluate this just as it's written, but I think it's going to make life easier to clean stuff up a little bit. This negative and this negative makes this term positive, and this term just has one negative, so it's negative. So I have negative 1 over 2u squared, because u to the negative 2 power is the same as u squared down in the denominator. And then in this term, I have 1, positive 1, again, because the negatives cancel, over 3u cubed. And that needs to be evaluated from 0 to 1. But because those bounds of integration are still written in terms of x's, before I go plugging them in, I need to change my u's back to x's. That's doable because I know u is 1 plus the square root of x. So replacing the u's with 1 plus the square root of x in each of these terms, I end up here. Note that I can now drop the x notation over here because it's implied that these bounds are in terms of x if it doesn't specify otherwise. And since I've changed my u's back to x's, now my bounds of integration match my variable of integration. And now I can go plugging in ones and zeros, which I think will work out fairly nicely. Not super nice. Plugging in ones over here. Let's see, the square root of 1 is 1. 1 plus 1 is 2. 2 squared is 4. 4 times 2 is 8. So I think this one ends up being negative 1/8. Similarly over here, square root of 1 is 1. 1 plus 1 is 2. 2 cubed is 8. And then 3 times 8 is 24. So I get negative 1/8 plus 1/24. And then from that, I want to subtract what I get when I plug in zeros. Square root of 0 is 0. 1 plus 0 is 1. 1 squared is 1. I think this ends up being negative 1/2. Similarly, over here, I end up getting positive 1/3. This is negative 3/24. This is 1/24. So together, they give me negative 2/24. In other words, negative 1/12. This is negative 3/6. This is positive 2/6. So together, they give me negative 1/6. But I'm subtracting that negative 1/6. So I got plus 1/6 here. 1/6 is 2/12. Negative 1/12 plus 2/12 is positive 1/12. 1/12 times 2 is 2/12, which is 1/6. There's like a 50-50 shot that I didn't screw up something with the fractions in there. But if I did everything right, I think this ends up evaluating to be equal to 1/6. Really, I wasn't trying to refine your fraction addition and subtraction skills. What I was trying to show you is the substitution part. You could argue that maybe I should have stopped after I got to, I don't know, like right here and called it good. But I wanted to give you one example with the definite integral that was really hard since we didn't have as many of those in these videos.